So I accidentally rotated my computer. Hopefully I'll be able to splice these back together. If not, well, welcome to 11.4 part 2. All right, so I was talking about the derivative of a function at a versus at x. Again, mainly that's just a philosophical difference where a is just a single point, x is a variable. And so when we're talking about that, like up here we were saying at when a equals 1 or a equals 4, um, here we're just going to let it be x. We're not going to plug in anything for that number. But the definition is still exactly the same. Now, again, we can kind of look at this intuitively. Um, if I, let's go back to my website that I looked at before. All right, so let's look at the derivative as a function. So um, now we got the same graph that I had before. As I slide C, notice my tangent line's moving around, all around. But so what we're going to look at is, notice right here, uh, that red point right there is exactly the value of the slope, right? So the slope of that line is about 1.5. If I look over here, my slope here, it's locking onto 3, but you can kind of see it's 0 where it's completely horizontal, it's 0. So, and then we get negative, and then you can kind of see again. That's the numerical value of the slope at each point. Now, one other thing you'll notice at this point right here, this little cusp, the derivative does not exist because the limit from the left is this line right here, the limit from the right is this line right here, and they don't line up. But so when I talk about the derivative at a point, it's just that value. It's just a numerical value. So like there, it's about 1, maybe just a little over 1. So there, the slope, the derivative is about 1. Now, if I want to talk about the derivative of a function, we're going to do that everywhere. And if I can do this nice and slowly, some of the spots where it locks on, it's going to have little jumps. It's not supposed to. See if I can get it. But the only jump it's supposed to have is that big one at x equals 1. But you can kind of see as I fill this all in, this red dot here, or this red curve, that is the derivative as a function. Okay, so the nice thing about having the derivative as a function is once I do that, I can figure out the slope at any point on my line. So let's go ahead and look at what this is. So we did x squared minus x before. We're going to do something fairly similar, x squared minus 5x. So let's find f prime of x. All right, so, and you'll see in part B why this is useful to do it this way. And there's many more examples of how it's useful. So f prime of x, again, by definition, is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. Now, let's again color code this guy. So f of x plus h. Well, I'm going to go ahead and plug that in. That means I'm going to plug in x plus h everywhere I have an x. So x plus h goes in there, x plus h goes in there. So I'm going to have x plus h squared minus 5x plus h. Now, f of x is just what I had there, and that's what f of x is, right? So it's x squared minus 5x. Now, common mistake is not having this in parentheses. Make sure you have, when you're subtracting f of x, you have to have it in parentheses. It's a very, very common mistake. So all of that's over h. Now we just go ahead and expand this. And x plus h squared, we use our good old binomial theorem that we learned not very long ago. It turns into x squared plus 2xh plus h squared minus 5x minus 5h minus x squared plus 5x. All of that over h, and I got my limit sitting out in front. So I just expanded all that, distributed the minus sign through, and now let's look for cancellation. We should get a lot of cancellation. So x squared minus x squared goes away. Minus 5x plus 5x. That's not a very good x, but those cancel. And so now I've got equals limit of 2xh plus h squared minus 5h over h. And if I've done this right, everything should have an h, and I should be able to cancel an h from everything. So let's go ahead and do that. We got an h everywhere, so let's cancel one h from everything. And so I end up with limit of 2x plus h minus 5. And remember, that limit is h goes to 0. So notice what happens as h goes to 0? Well, that equals 2x minus 5. Now, when we're talking about the derivative as a function, it's okay for it to have an x in it. Most times it will. If it's a line, it won't, but most times it will. So um, now we got our derivative. So if I want to write my final answer, if you could write f prime of x equals 2x minus 5. So that's representing the derivative. So the nice thing is part B, if I want to do this part B before I had done part A, I would have to go through the process I did up here, where I'd plug in 4, like how I plugged in 4 there. I'd have to plug in 1, and then I'd have to plug in -3 and go through the whole, or sorry, -1 and 3. So I'd have to plug in -1 there, and then I'd have to do the whole thing again and then plug in 3. So I go through the whole process twice. And if I had to plug it in multiple times, like 5 times, I'd have to go through it 5 different times. When I do it with just plain old x here, now it's super easy. If I want to find what f prime of -1 is, well, let's plug it in. 2 times -1 minus 5. So I get -7. Do I want to know what the slope at 3 is? Well, I can plug it in. 2 times 3 minus 5 equals 1. And so now I can find out the slope at any point very, very quickly and easily. All right, so the average rate of change, again, we talked about this. This is our formula. So that's f of a plus h minus f of a over h. And then this is f. I don't really like some of this terminology, or I think they might be looking for an x here. But because I don't really like this combined with that. So let's just ignore that right there. All right, so f prime of x is that right there. So those are basically our two things. The only difference between them is that limit as h goes to 0. Like I said before, instantaneous rates of change are very, very useful. So if I know my position at any given time, I know the derivative of that. So the instantaneous rate of change of position, we call that velocity, right? We have the name for that. How fast my distance is changing is my speed, but if we include direction, it's called velocity. So derivative of position, notice I say position, not distance, but the derivative of position is velocity. So the function f of x equals x cubed describes the volume of a cube. So where the length of a side is x. So find the average rate of change of the volume with respect to x as x changes from 4 to 4.1 and from 4 to 4.01. All right, so the whole idea here is, remember, we're going to use this top equation, f of x plus h minus f of x over h. And in this case, like for this first one right here, h is going to equal 0.1. Right? That's the difference. From 4 to 4.1 is 0.1. So I end up with 4.1 cubed minus 4 cubed over 0.1. So if we go ahead and do that real quick, 4.1 cubed minus 4 cubed. I don't know why I did that one in the calculator, but all right, so I get that divided by 0.1. That's going to multiply by 10, so I get 49.21. And these are in inches, so the volume, so inches cubed. Now if I do to 4.01, h is now going to equal 0.01, and I'm going to have 4.01 cubed minus 4 cubed over 0.01. So if we do that, 4.01 cubed minus 4 cubed, and then we're going to multiply by 100. Oops. Minus 4 cubed, and we're going to divide that by 0.01. Make sure you don't you do them in separate steps or use parentheses, right? Don't just do it all in one line without parentheses or using, your alpha, doing this guy right there. All right, so I get 48.1201. Now, if I were just to guess haphazardly from this, I might be right, I might be wrong, but it looks like this number is getting closer to 48. So if I had to guess, it's going to be, if I find the instantaneous rate of change of the volume, that is, I'm going to get 48. But let's go ahead and do it. So first off, f prime of x, remember, is equal to the limit as h goes to 0 of f of x plus h minus f of x over h. And you could do it two different ways. You could just plug in 4 right now, or you could wait till the end and plug in 4. It doesn't really matter. I'm going to do it with x just because in the future you'll probably do it more frequently just to find the function. So I get the limit, and now I'm going to take x plus h, and I'm plugging it in to x cubed, right? Remember, f of x is equal to x cubed. So I take x plus h and plug it in there. So I get x plus h cubed minus x cubed over h, which equals, again, use our good old binomial theorem, and we get x cubed plus 3xh, or x squared h, plus 3xh squared plus h cubed minus x cubed over h. Get x cubed minus x cubed go away. And so I get 3x squared h plus 3xh squared plus h cubed over h. And I can cancel one h from everything, right? Everything has an h, so there goes away 1, 1. Now I'm left with 1 there, and I'm left with 2 there. So I get equals limit of 3x squared plus 3xh plus h squared. And remember, h is going to 0. So what's the limit of 3xh as h goes to 0? That's 0. That's 0. So I get 3x squared. Change that color here. So I get 3x squared. And so I want to know when x equals 4. So f prime of 4 is equal to 3 times 4 squared, which is 3 times 16, which is 48. And that's, again, inches cubed per, I labeled this wrong, per, it doesn't say per or anything, I guess. But yeah, so it's per inch. So let's just say inches cubed. All right, so that's how much it changes. That's how fast the volume is changing at that point in time. All right, so the instantaneous velocity, suppose that a function expresses an object's position s of t in terms of time t, the instantaneous velocity. This is, again, exactly the same function. The only difference is and this is, that should be, there's a few typos on here. That should be s prime of a. That's going to equal s of a plus h minus s of a all over h. Exactly the same formula that we're using up here, right? Exactly the same as this guy. So no sense trying to memorize a new one. It's just the same function, just different labels. So if I want to find the instantaneous velocity of the ball 2 seconds after it's thrown, well, let's find s prime of t, which is going to equal the limit as h goes to 0 of negative 16 t plus h squared plus 48 t plus h plus 160 minus, and then that whole thing again. So again, all that stuff I've written so far came from plugging in t plus h in all of those. And I could have plugged in 2. I just like to do it with the variable so we get more practice. It's a little bit tougher algebraically at first when we're not too confident about it, but eventually, once you do enough, they're basically the same difficulty. So I subtract the original function, so 16t squared, negative 16t squared plus 48t plus 160 all over h. And so now I multiply all this out, so I get negative 16t squared minus 32th minus 16h squared plus 48t plus 48h plus 160, and then I'm going to get plus 16t squared minus 48t minus 160. That's all over h. Now again, that looks super long and super complicated, but luckily what's going to happen is minus 16t squared plus 16t squared plus 48t minus 48t plus 160 minus 160. And you should get lots of cancellation like that on all these. So I get minus 32th minus 16h squared plus 48h, and that's all over h. Now everything here has an h, so cancel one h from everything. I'm left with equals limit of negative 32t minus 16h plus 48. And remember, that's h goes to 0, and so I end up with negative 32t plus 48. And there's another benefit of doing it this way instead of plugging in 2, is notice part B, it asks for another instantaneous velocity. Well, now I've done all the hard work. I don't have to do it again for part B. I just have to figure out what the time would be. All right, so S prime of 2 is equal to negative 32 times 2 plus 48. So that's negative 16. And this is in feet per second. All right, so what is the instantaneous velocity of the ball when it hits the ground? So now we got to use our noggins a little bit, use some stuff from back in chapter 2 when we talked about quadratics. Remember, we need to figure out where does that hit the ground. So to find that out, we need to find out what t is, how long it's in the air. So I'm going to set the position, not the velocity, not the derivative, but the original function. I'm going to set this guy equal to 0 so I can find out when it hits the ground. So negative 16t squared plus 48t plus 160. And let's go ahead and divide both sides by negative 16. So I can get t squared minus 3t minus 10. So I get t minus 7. Minus 7, I mean t minus 5. That's what I meant to say. T plus 2. So notice I get it hits the ground at t equals 5 because it's not going to hit it at negative 2, right? So we hit the ground at t equals 5. So now the nice thing is I get to plug 5 in to this guy up here. And so I get S prime of 5 is equal to negative 32 times 5 plus 48. And so negative 32 times 5 is negative 160 plus 48 gets me negative 112 feet per second. And there you go. I actually might leave these videos separate so that way it's not one humongous thing. So yeah, I expect questions in class, but hopefully that's enough to get you started.